Tortuga Field Case Study by Lauren Price, Dino Bueller, Ali Alisawi, and Jason Jalme. The Tortuga oil field can be found in the Gulf of Mexico. Because this well has no production history, my classmates and I will compute the predicted production rates while varying modifiable components. Because the reservoir is in the Gulf, the well, flowline, and manifold are all subsea, at a depth of 1,935 feet from the waterline. The two wells connect to the one manifold, which then connects to a single flow line. The flow line connects the manifold to the host platform, where the separator can be found. First, the permeability of the Tortuga reservoir is very large, at 600 millidarcies, which is advantageous to our flow rate and thus production. We know this through the pseudo-steady equation shown. As permeability, K, increases, flow increases as well. However, the reservoir's damage area has a permeability of 100 millidarcies and a damage length of 5 inches. We will discuss the implications of this lower permeability later. Other reservoir parameters include the initial pressure at 13,000 psi and reservoir temperature at 225 degrees Fahrenheit. Porosity is 25%, and the wells drain an area of 1,500 acres per well. Each well has a calculated drainage radius of 4,560.5 feet. The parameters for fluid are listed below. 5 million stock tank barrels of hydrocarbons in place, 10% water cut with 20% reservoir water saturation, gas-oil ratio at 900 SCF per STB, oil at 30 degrees API indicating black oil reserves, gas gravity is 0.7, and formation water specific gravity is 1.1.
The following assumptions have been made. Production rate remains constant for the period of 1 year. The two wells are perfectly identical. 100% of the hydrocarbons in place are able to be recovered. The Pipesim apparatus of the sink is our separator, and the separator is considered a pressure barrier. Because the fluid is 30 degrees API, we assume black oil and use black oil correlations. Because of this, there is not composition change. Transient time is negligible in comparison to the overall lifetime of the well.
Okay, so now we will be discussing the analysis and results of our base case. To keep all of our tested base case parameters satisfied, we will run this scenario with a separator pressure of 500 psi, a tubing inside diameter of 4.5 inches. Our wellbore radius is at 6 inches. We ran this case with a cased well down to 18,250 measured depth and a perforation at 17,500 feet. We also have a choke size of 1/4 inch or 16/64. We first ran a nodal analysis at the bottom of the well and determined that our initial flow rate is approximately 2,004 barrels per day. This is at a bottom hole pressure of 12,198 psi. This flow rate was calculated neglecting our 65-hour transient time and assuming that the well is flowing in pseudo-steady flow throughout the life of the well. The reason we neglected the transient time was due to the fact that it was very small into comparison of our 10-year production time. So on our first graph, we have our results for our nodal analysis at the bottom of the well with a average reservoir pressure of 13,000 psi. You can see that our first data point converges at the 2,003.995 barrels per day as our flow rate. Our TPR is shown by the green line on the graph, and as our IPR is represented by the red line. We also have included a zoomed in version of this graph with our TPR in red and our RPR in blue. On this slide, we have put together our results for 10-year production for our base case scenario. As you can see, at year one, our average reservoir pressure starts at 13,000 psi. We got a flow rate of about 2,004 barrels per day. Now, I did mention before that this is for one well, so our 2-well production would be approximately 4,008 barrels per day. And this is at a bottom hole pressure of about 12,883 psi. At this specific flow rate, it will give us a total yearly production of about 1.4 million barrels. We also use these flow rates and multiplied it by our pressure decline, which is 0.2 psi per year per barrel per day. At this rate, we calculated the decline and subtracted from our original P-bar and then repeated the process over a period of 10 years. We found that over a 10-year period, our cumulative production is approximately 11.2 million barrels of oil. And since our reservoir only holds about 5 million barrels, we depleted our well in 3.67 years. On this graph, we have showed our period of 10 years with our flow rate depicted in the orange line, and in the blue line shows our production over the cumulative production over each year for 10 years. You can see at this point on our graph is where we've reached our 5 million barrels, right around 3.5 years. This is where our well is technically depleted.
Our process of turning the open hole problem we were given and adding a completion was quite a task. After changing some variables in Pipesim, we decided to enhance our well by doing a partial completion. When a well is partially completed, the producing height that is open to the formation, HW in the picture presented, is much smaller than the reservoir height, H, in the picture presented. Partial completions are generally used to prevent water or gas from entering the perforation zone around the wellbore. Muskrat derived an analytical solution to calculate the effect of a partial completion, and this is the method we used to add the completion to our base case. We started by calculating our partial completion skin factor from Muskrat's relationship. The completion was started from the top of the well, and all parameters within the equation were given, with the exception of HW. HW, as previously mentioned, is the producing completion height open to the formation. Since this has to be less than our reservoir height of 80 feet, we decided to use a constant HW value of 60 feet. After the calculations were completed, a larger positive skin effect was produced. Originally, our skin factor was 3.02, and after the completion was added, it increased by 10.87 to give us a new skin value of 13.89. Unfortunately, positive skin is not good for production, so our idea of doing a partial completion was not the best. We compiled cumulative production results over 10 years using the new skin factor. Overall, our cumulative production with this new skin factor was calculated to be 11,146,892 stock tank barrels. This is a drop from our base case cumulative production, which was 11,205,509 stock tank barrels. We would lose roughly 58,617 stock tank barrels of oil if we decided to partially complete our well.
The choke is an integral part of the production system. This device contains an opening which is used to control flow rate through the pipe, as well as downstream system pressure. In our well, an adjustable choke was installed which allowed us to control the opening size of the device. Therefore, we were able to modify the flow rate and downstream pressure. In the base case of our well, the original opening size of the choke was set to 1/4 of an inch. With this choke opening, our calculated flow rate was found to be 2,004 stock tank barrels per day. In order to fully understand how adjusting the choke controls the flow rate, the following set of equations have been derived. We start with the equation for the pressure drop due to the kinetic energy. This equation shows the direct proportional relationship between the pressure change and the change in velocity of the flowing mixture. Looking further into the equation for the change in velocity, we see velocity equals the volumetric flow rate divided by the cross-sectional area. The main assumption we are making for this equation is that volumetric flow rate is constant. After assuming this, we can further develop the cross-sectional area piece of the equation. Cross-sectional area for a pipe is equal to pi times diameter squared divided by 4. Inserting this equation into the equation for flow rate, we are able to see that flow rate is now inversely proportional to diameter squared. When this new equation for flow rate is plugged back into the equation for pressure drop due to the kinetic energy change, the pressure drop becomes inversely proportional to diameter raised to the 4th power. Therefore, as we increase the size of the diameter, or in other words, open the choke, we decrease the pressure drop within our tubing system. This is exactly what we want to do, because when we minimize the pressure drop within the tubing, we maximize our production. In our well, we used different choke openings that were both smaller and larger than the initial opening of the base case, which used 1/4 of an inch. At first, the openings used ranged from 1/8 of an inch to 1 inch. While choosing choke openings, we had to keep our maximum separator liquid handling capacity in mind. The separator we are using can only handle up to 10,000 stock tank barrels of oil per day. Therefore, we cannot choose a value which goes over this limit, or else we will experience issues at our separator and possibly cause our separator to quit functioning. Due to this restriction, our best case scenario for choke opening size was listed as 3/8 of an inch. This gave us a maximum flow rate of 8,837 stock tank barrels per day. Overall, alternating your choke position is one of the most effective ways to increase well production. This is due to the fact that adjusting the choke does not cost money and does not require any investment in new equipment for the rig.
The separator component of a well is usually placed at the end of the production tubing. This massive cylindrical piece of equipment plays a vital role in capturing hydrocarbons from a well stream. It operates on simple concepts such as gravity and differential density. It is within this tank that oil, gas, and water are separated from each other. There are two main types of separators used within the industry today. These include the 2-stage separator option as well as the 3-stage separator option. The later option being used if you are producing water in your well stream. Like mentioned before, gravity is a key component within the separator because it allows the fluids to naturally separate out from its single original well stream condition. During separation, heaviest fluids end up at the bottom of the tank, while lighter fluids rise to the top. In our calculated well, our separator was located on an offshore platform which was 82 feet above the surface of the water. The well stream fluids traveled at a total distance of 12 miles from the time they exited the wellhead to the time they entered the separator. To make our simulator calculations easier, we used a sink within Pipesim to represent our 2-phase separator. While this was not the most practical method, and because we used a sink, we had to assume single-phase oil within our well stream throughout production. For our initial setup, the separator pressure was set at 500 psi. When testing different separator pressures, we used values both higher and lower than our original value. The values we chose ranged from 14.7 psi, atmospheric pressure, all the way up to 2,000 psi. Because we assumed single-phase oil, all of the inflow performance curves for each pressure overlapped each other. Therefore, changing the pressure within the separator made no difference for us. It kept us at a constant flow rate of 2004 stock tank barrels per day.
Wellbore radius is a parameter which affects the tubing performance relationship curve. When modeling our reservoir within Pipesim, we made the assumption that as wellbore radius changes, tubing radius changes as well. Tubing is an important factor which governs the shape of the TPR curve. When determining tubing size, you want to find the size which has the smallest energy consumption to lift the flow, in other words, the smallest dP over dZ. You also want to pick a tubing size which will ensure the longest flowing time for your well. When considering the effects of changing wellbore radius in Pipesim, we opted to delete our tubing and use the casing diameter as the changing wellbore radius. We had to use this workaround method because Pipesim would not give us the option to just change our wellbore radius. For our results, we tested 8 smaller inner diameters of the wellbore radius. The 2-inch diameter wellbore represented by the standalone red TPR curve gave us the lowest flow rate of around 1,878 SCB per day. This is due to the increase in the frictional factor through the wellbore. This flow in the wellbore lost velocity to this frictional component. Therefore, the dP over dZ value increased in the wellbore. The other 7 diameters developed TPR curves which almost overlaid each other. This result shows that sometimes changes in the wellbore diameter can have only a slight effect on your production rate. It may not be worth the hassle and the cost to increase the wellbore diameter.